The 1919 Nobel Prize in Physics was awarded to this gentleman, Johannes Stark. Not Tony Stark, or Tony Stark's dad, but this Stark, for his discovery of the Doppler effect in canal rays and the splitting of spectral lines in electric fields. That's a big pile of science all in one sentence. And it's going to take a little bit to explain this one, so I hope you'll bear with me to the end. And this particular prize and this particular scientist is something that I think we all need to take a look at very carefully and think about how this applies to the modern day situation we find ourselves in on more than one occasion when we're trying to examine science on a particular topic area. So I hope you'll bear with me till the end. And if you haven't already, please click subscribe and like on the video. That really does help the channel and the algorithms kind of get seen by more people. So let's dive in and figure out what that gigantic pile of science really means. Well, this particular prize has a lot to do with plasmas. Now most people are used to 3 different states of matter. That's a solid, a liquid, or a gas. And we see those every day. But plasma is a 4th state of matter, and it's really just the presence of a significant number of charged particles. And that could be in one of the little toys like you see on the screen, or that could be in the sun, or that can be in a lightning bolt. It could be in a nuclear fusion reactor. Plasma is what this prize is all about, and how to actually understand what's going on inside of plasma, because if you want to effectively use it for something, you need to understand it. And if you don't understand it, you can't engineer the right product, or you could build something that could actually hurt people. So what this prize did was it allowed us to understand what's inside of plasma, but let's look at how it did that. Now, every atom in the world has a nucleus and an electron cloud. Sometimes those electron clouds have 1 electron, such as hydrogen. Helium has 2, carbon has more. The bigger the nucleus, the bigger the atomic number, the more electrons it has. Now, to be in a plasma state, you have to get those electrons off of that nucleus. To be in an excited state, you only have to get them further away. So what that means is when an atom is in its ground state, or its most sort of stable, not excited, not being pounded on with energy, the electron is the closest to the nucleus it's going to get. The more energy you put into that atom, the more excited that electron becomes, and it goes into what's called an excited state. And how to get it from one of those states to another is you have to put some amount of energy in. Now, those electrons only have quantized, notice that word again, quantum, or quantized, 1, integer versions of excited states. It can't be at a halfway excited state. It's either all the way excited or it's not. And to understand that for each atom was something nobody really understood before this point. So if we're going to get to a plasma state, more importantly, a controllable plasma state, which is fantastically important for lots of different kinds of engineering, including nuclear fusion, you have to fully understand what those excited states are. Now, how do you get from one of those states to another? Well, in this case, you just push in a bunch of electricity, or you push in a bunch of power in some way, whether that's heat. You could do it in a lot of variety of different ways. But what does that really tell you, and how do you tell when you're in one excited state versus another? You can't just look at hydrogen gas and go, yeah, that's in the 3rd excited state. You have to have a method to do that. Now, as you put more and more electricity into a gas or into an atom, you'll get light to start to appear, or you'll get UV or IR to start to appear. You'll get this electromagnetic radiation that comes out, and that comes out in discrete lines. Those lines are known as the spectra. You can pick that up with a device called a spectrometer, and when you measure that with a spectrometer, you can look at those spectral lines, you can do some math, and you can figure out exactly what's in your sample. So let's say, for instance, you have a gas, and that gas has all kinds of things in it, whether that's carbon gas, a little bit of something with carbon in it, a little bit of hydrogen, a little bit of helium. You excite it, you get it moving into a plasma, and you're going to see these spectral lines appear. And those spectral lines will be characteristic of different atoms. And then you can calculate what atoms you have and what their excited state is. Do you have it in a state where carbon only has 5 electrons left on it, so it's positively charged now, and there's an electron floating around? Do you have it stripped down to where there's only 4 electrons, or 2 electrons, or 1 electron left on? So now you have a positively charged atom, or what's known as an ion, and a bunch of electrons kind of hanging around in this little soupy space called a plasma. And from these lines, you can actually tell what's going on inside your plasma. And in order to use your plasma for something specific, you need to understand those lines. And more importantly, you need to understand what pollutants might be in your lines. And if you're going to use a plasma for things like disposal of biological waste or any number of biological hazards, you really want to understand what's in that plasma. And have you knocked all the molecules apart, the dangerous molecules, have you knocked them back into their constituent pieces? And make sure they don't recombine into something dangerous. So this is a very important bit of technology. Although it is very fundamental science, it's very, very important to the world we live in today. Now, that's what he did to win the prize. There is another part to this man that really does need to be discussed. And I think this will reflect on things that go on in our modern space just a little bit. Now, remember, all of this work was done in in a time period that was around, World War I, before World War II started. In fact, significantly before World War II started, because World War I was just coming to an end at this point. So this work was done during the war, but it's important to remember that scientists do have lives outside of that. So let's take a look at this man outside of his science career. After World War I ended, a German physicist like Mr. Stark here needed to be involved in their craft, right? Everybody wants to be involved in their craft. The trouble is, Germany at that point in time had no money. They were having rapid inflation. They were in all kinds of trouble after the war. They had all kinds of economic problems. They had societal problems. It was just not a great place to be. So he started trying to figure out how he could make a difference in Germany in that time period in between World War I and World War II. Now remember, he won the prize in 1919, and in 1924 the atrocities of World War II had not happened yet. But in 1924 he chose to throw his support behind a young Adolf Hitler. Let's not get into whether that was a good thing or a bad thing. I think we can all agree that was a terrible thing to do. Hitler rising to power was the worst mistake in the last 200 years, and possibly much further back than that. He was also a rabid anti-Semite. He was against Jewish scientists in a lot of ways. Now, does that make his science less important? No, it doesn't. It just makes some of his personal choices questionable in nature, and in fact, let's just say atrocious in a few ways. But what goes on in the modern sense when it comes to science in some cases is we almost take a litmus test to see which side of science we're going to fall down on. It's like, well, I'm on this side of the political spectrum, on that side of the political spectrum, therefore this is my scientific belief versus that being my scientific belief. The trouble is, science doesn't believe in a political spectrum, and scientists shouldn't either. Scientists should just stay out of politics, especially when it comes to impact their careers. You can do anything you want in your personal life. I don't really care where people vote. And if somebody wants to throw their weight behind a politician, that's fine. But I don't think it should degrade from their science in any fashion. And also, your politics should not enter the scientific world. The scientists themselves can go deal with politics all they want. That doesn't bother me in the least. But your politics should not define your science in any way. And I think that's something that really does speak to the modern world, that we need to separate those two things. Scientists need to just be scientists. Politicians need to be politicians. If a scientist wants to go deal with a politician, that's great. Good on you. But our scientific beliefs should not be driven by our politics. They should be driven by data, and they should be driven by scientific conclusions, not based on a political agenda. Everybody have a great day, and thank you for listening.